Our galaxy, a place filled with countless mysteries and wonders beyond our wildest imaginations. Created from what seems to be nothing, our galaxy is just one among potentially hundreds of millions we haven't yet seen. Floating in the vast universe, these galaxies, each with their own secrets, all share one unanswered question. How do they form from what appears to be nothing? Introduction to the universe. The universe, an ever-expanding mix of galaxies, stars, planets, and myriad forms of matter and energy, presents profound mystery that has captivated humanity for centuries. At the heart of modern cosmology is the understanding that the universe began approximately 13.8 billion years ago with the Big Bang, a colossal explosion that marked the inception of everything we know. This event set into motion the expansion of space, creating the cosmic web we observe today. Scientists have gleaned much about the universe's composition, revealing that ordinary matter, the stuff making up stars, planets, and us, constitutes a mere 5% of the universe's total mass and energy. The remaining 95% is a mysterious concoction of dark matter and dark energy, invisible forces that govern the universe's structure and expansion, yet elude direct detection. Delving deeper, the universe's vastness is almost beyond comprehension, stretching over billions of light years across. This immensity houses an estimated 2 trillion galaxies, each a collection of billions of stars and untold planets, offering a humbling perspective on our place in the cosmos. The laws of physics, consistent throughout the universe, govern the motion of galaxies, the life cycle of stars, and the intricate dance of particles at the quantum level. These laws have allowed scientists to predict cosmic phenomena with astonishing accuracy, from the paths of planets to the behavior of black holes, those enigmatic entities whose gravitational pull is so strong that not even light can escape. In this cosmic journey, the role of dark energy in accelerating the universe's expansion poses a tantalizing puzzle. Discovered through observations of distant supernovae, dark energy works against the gravitational pull of matter, driving galaxies apart at an accelerating rate. This discovery has profound implications for the fate of the universe, suggesting a future in which galaxies drift ever farther apart, leading to a cold, dilute cosmos. The Big Bang Theory stands as a cornerstone of modern cosmology, offering a compelling explanation for the origin and evolution of the universe. It posits that the universe began as an extremely hot and dense point approximately 13.8 billion years ago and has been expanding ever since. This theory is supported by a wealth of scientific evidence, including the observation of the cosmic microwave background radiation, a faint glow left over from the early universe, which provides a snapshot of the cosmos just 380,000 years after the Big Bang. This radiation, discovered accidentally by Arno Penzias and Robert Wilson in 1965, has a uniform temperature throughout the universe, confirming predictions of the Big Bang Theory and offering concrete evidence of the universe's hot, dense origin. Another pillar supporting the Big Bang Theory is the observation of the redshift of galaxies, indicating that they are moving away from us and, by implication, from each other. This discovery, made by Edwin Hubble in the 1920s, revealed that the universe is not static but expanding. The farther away a galaxy is, the faster it appears to be moving away from us, a relationship now known as Hubble's law. This expansion is a key prediction of the Big Bang Theory and suggests that the universe was once much smaller, hotter, and denser than it is today. Moreover, the theory elegantly explains the relative abundances of light elements such as hydrogen, helium, and lithium observed in the universe. According to Big Bang nucleosynthesis, these elements were formed in the first few minutes after the Big Bang, as the universe cooled enough for protons and neutrons to combine into nuclei. The predicted abundances of these elements closely match observations, lending further credence to the Big Bang Theory. Despite its widespread acceptance, the Big Bang Theory also raises profound questions and puzzles. For instance, it does not explain what preceded the Big Bang or what lies outside the observable universe. It also introduces a concept of cosmic inflation, a rapid expansion of a universe that occurred fractions of a second after the Big Bang, to solve the horizon and flatness problems. This inflationary period predicts that the universe should appear flat and uniform on large scales, which is consistent with observations of the cosmic microwave background radiation. Following the Big Bang, the universe embarked on a monumental journey of expansion, transforming from an infinitesimally small point to the vast cosmos we observe today. This expansion can be likened to a balloon being inflated, where galaxies move away from each other as the space between them grows. In the earliest moments, the universe was a hot, dense soup of particles and radiation, too energetic and chaotic for atoms to form. As it expanded, this primordial fireball cooled, allowing quarks to combine into protons and neutrons, which then formed the simplest nuclei, predominantly hydrogen and helium, through the process of nucleosynthesis. This phase of rapid expansion, occurring less than a trillionth of a second after the Big Bang, is theorized to have been driven by cosmic inflation. Cosmic inflation posits that the universe expanded at a rate much faster than the speed of light during this brief period. This exponential expansion smoothed out the distribution of energy and matter across the cosmos, laying the groundwork for the uniformity we observe in the cosmic microwave background radiation. It's a concept that challenges our everyday understanding of physics, suggesting that the rules of the cosmic scale can differ vastly from those governing our observable world. As the universe continued to expand and cool, gravity began to sculpt the distribution of matter, pulling particles together to form the first stars and galaxies. These celestial bodies acted as cosmic furnaces, forging heavier elements in their cores and releasing them into space when they died, seeding the cosmos with a building block for planets and life. The universe's expansion is not uniform. It's influenced by the distribution of matter and energy, leading to the formation of a web-like structure of galaxies and galaxy clusters, interspersed with vast voids. This expansion is still ongoing, with galaxies moving away from us in all directions. The discovery that this expansion is accelerating was a groundbreaking revelation, hinting at the presence of dark energy, a mysterious force that permeates space and exerts a repulsive force, counteracting gravity. The exact nature of dark energy remains one of the most pressing mysteries in cosmology, with researchers striving to understand how it will influence the future evolution of the universe. The early universe. The first second after the Big Bang presents a timeline of incredible transformations that laid down the fundamental structure of our universe. Imagine the universe at its inception, an unimaginably hot and dense point. Within a fraction of the first second, the universe began expanding rapidly in an event known as inflation, stretching far beyond the realms of our current comprehension, setting the stage for everything that would follow. This initial expansion was so rapid that it took less than a blink of an eye for the universe to grow from smaller than an atom to a size larger than a galaxy. As it expanded, the temperature began to fall, allowing the fundamental forces of nature to start separating from each other. During the first tiny fraction of a second, gravity separated from the grand unified force, marking the first major transition in the early universe. Following this, as the universe cooled further, the strong nuclear force, responsible for holding the nucleus of an atom together, separated from the electroweak force, which is a combination of the electromagnetic force and the weak nuclear force. This separation marked the universe's transition from a state where all forces were unified to a state where the distinct forces we observe today began to emerge. Within the first second, the universe cooled enough for quarks, the building blocks of protons and neutrons, to start combining. These quarks initially existed in a freeze state due to the extreme temperatures, but as the universe expanded and cooled, they began to bind together, forming protons and neutrons. This process, known as baryogenesis, was crucial for the formation of matter as we know it. Simultaneously, the universe was filled with a dense, hot plasma of quarks, electrons, and neutrinos. As it continued to expand and cool, interactions between these particles started to change. This cooling period allowed the strong nuclear force, one of the four fundamental forces of nature, to dominate over the thermal kinetic energy that kept quarks apart. When this happened, quarks began to stick together in stable groups known as hadrons. Protons and neutrons are types of hadrons. A proton is made of 2 up quarks and 1 down quark, while a neutron consists of 2 down quarks and 1 up quark. The specific combination of quarks determines the properties of the particle, such as its charge. Protons are positively charged, and neutrons are neutral. This distinction plays a vital role in how atoms and molecules, the building blocks of matter, are formed and interact. The formation of protons and neutrons from quarks was a critical step in the early universe's evolution. It marked the beginning of the end for the quark-gluon plasma state, and the start of a universe filled with matter as we know it. Once protons and neutrons formed, they could begin to come together, forming the nuclei of the simplest elements, a process known as nucleosynthesis. This sequence of events set the stage for the chemical complexity necessary for the stars, galaxies, and life to eventually emerge. As we continue to unravel the universe's early moments, the role of the fundamental forces becomes a pivotal chapter in the cosmic saga. These forces, which are gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, acted as the architects of the universe, sculpting the raw materials created in the aftermath of the Big Bang into the complex structures we observe today. In the universe's first moments, all forces were unified into a single force. As the universe expanded and cooled, this unified force began to break apart in a process known as symmetry breaking. The first to separate was gravity, which plays a crucial role in shaping the large-scale structure of the universe by influencing the motion of galaxies and clusters of galaxies. Despite being the weakest of the four forces, gravity's influence grows with mass and distance, making it the dominant force on a cosmic scale. Following gravity, the strong nuclear force separated. This force is responsible for holding the nuclei of atoms together, overcoming the repulsive electromagnetic force between the positively charged protons. It was during this separation that quarks began to combine into protons and neutrons, as we previously explored. The strong force ensured that these particles could form stable nuclei, setting the stage for the creation of the first atoms. The weak nuclear force and electromagnetism were the next to differentiate as the universe continued to cool. The weak force is key in the process of nuclear fusion and radioactive decay, playing a vital role in the life cycles of stars and the synthesis of elements heavier than hydrogen. Electromagnetism, on the other hand, governs the interactions between charged particles. It's the force behind light, electricity, and magnetism, shaping the behavior of atoms and molecules, and thus the chemistry that underpins all of life. Together, these forces dictated the universe's evolution from a homogeneous soup of particles to a structured, diverse cosmos filled with galaxies, stars, planets, and ultimately life. They determined the formation of the first hydrogen and helium atoms in a process known as recombination, leading to the universe's transparency to light and the release of the cosmic microwave background radiation, a relic from this era that provides us with a snapshot of the infant universe. The interplay between these forces also drove the formation of stars and galaxies. Gravity pulled matter together, while electromagnetism and the nuclear forces govern the internal processes of stars, including nuclear fusion, which powers stars and generates the heavier elements essential for planets and life. Formation of atoms and molecules. Delving deeper into the mysteries of the universe, we pivot our attention toward the formation of the very first atoms, a seminal event that marked a turning point in the cosmic narrative. This process, known as recombination, occurred approximately 378,000 years after the Big Bang. Before this epoch, the universe was a hot, dense plasma of electrons, protons, and photons. The temperatures were so extreme that atoms could not form without being immediately torn apart by the rampant energy. As the universe expanded, it cooled down, allowing for the first atoms to emerge. Hydrogen, the simplest and most abundant element in the universe, was the first to form. This element, consisting of just one proton and one electron, marked the dawn of a new era in cosmic history. Helium atoms, slightly more complex with 2 protons, 2 neutrons, and 2 electrons, followed shortly after. These elements laid the foundation for the chemical diversity we observe in the universe today. The formation of these first atoms was a turning point that significantly altered the universe's structure and future evolution. With atoms now stable, they began to gravitate towards each other, slowly building the first stars and galaxies. This era set the stage for the complex chemical processes that would eventually lead to the formation of planets and life itself. Following the monumental formation of the first atoms in the universe, an equally remarkable phenomenon unfolded: the birth of the first molecules. This transition from solitary atoms to the earliest molecules marks a significant chapter in cosmic history, laying the groundwork for the complex chemistry that underpins the universe as we know it. As the universe continued to expand and cool, conditions gradually became favorable for these freshly formed atoms, primarily hydrogen and helium, to interact in novel ways. Hydrogen, with its single electron, was particularly predisposed to forming bonds with other hydrogen atoms. The emergence of molecular hydrogen, or H2, was a critical step forward. This molecule, though simple in structure, played a pivotal role in the universe's early chemistry. The formation of molecular hydrogen provided the first building blocks for more complex chemical reactions. It acted as a coolant, allowing gas cloud to collapse more efficiently under gravity, which in turn led to the formation of the first stars. These nascent stars were the crucibles in which the first heavy elements were forged, elements that would eventually give rise to the rich chemical tapestry that makes up planets, asteroids, comets, and all living organisms. The exact timing of the first molecule formation is a subject of ongoing research, but it is believed to have occurred a few 100,000 years after the Big Bang, following closely on the heels of atomic formation. This era set the stage for the intricate interplay of forces that would eventually lead to the universe's structure, from galaxies to planets, and the very essence of life itself. As we trace the cosmic lineage back to its origins, the roles of helium and hydrogen emerge as foundational to the early universe's evolution. These two elements, the simplest and most abundant in the cosmos, were instrumental in shaping the universe from its nascent stages. Their significance cannot be overstated, as they were the primary constituents of the primordial universe, setting the stage for all subsequent astronomical phenomena and the complex chemistry that characterizes the cosmos today. The Dark Ages. As the afterglow of the Big Bang began to fade, the universe entered a period known as the Cosmic Dark Ages, a time that lasted for about 380,000 years to a billion years after the universe's inception. During this era, the universe was filled with a dense, cooling fog of hydrogen gas, rendering it opaque and, in a sense, invisible to the kind of light we can now observe with telescopes. Without stars or galaxies to illuminate it, this epoch stands as an enigmatic chapter in cosmic history, a stretch of time when the cosmos was eerily silent and dark. The Cosmic Dark Ages are a critical period in the universe's evolution, laying the groundwork for the formation of the first stars and galaxies. As the universe expanded, the primordial gas that filled it began to clump together under the influence of gravity. These regions of higher density eventually became the nurseries for the first stars, known as population 3 stars. Unlike the stars we see today, these celestial bodies were massive, luminous, and short-lived, composed almost entirely of hydrogen and helium. The nuclear reactions within these stars eventually reionize the surrounding hydrogen gas, piercing the opaque veil of the Cosmic Dark Ages and bringing the universe into a new era of transparency and light. This transition, known as cosmic reionization, marked the end of the Cosmic Dark Ages and set the stage for the rich tapestry of structures we observe in the universe today. The light from these first stars and galaxies began to travel through the cosmos, gradually illuminating the once dark universe. This period is of intense interest to astronomers and cosmologists, as it holds clues to the formation of the first cosmic structures and the nature of dark matter, a mysterious substance that exerts a gravitational pull yet does not emit, absorb, or reflect light. Studying the Cosmic Dark Ages poses significant challenges, as the light from this period is exceedingly faint and difficult to detect. However, with advancements in technology and the advent of next-generation telescopes, scientists are beginning to pierce this veil. Observations of distant quasars and galaxies, along with the cosmic microwave background radiation, a relic from the Big Bang, provide valuable insights into this pivotal era. These studies not only shed light on the Dark Ages themselves, but also help us understand the fundamental processes that have shaped the universe from its earliest moments to the present day. Emerging from the Cosmic Dark Ages, the universe embarked on a transformative journey, culminating in the birth of the first stars and galaxies. This pivotal epoch, occurring roughly around 100 million years after the Big Bang, signifies a monumental shift in the cosmic narrative. Initially, the universe was a homogeneous soup of hydrogen and helium gas. However, subtle fluctuations in density, possibly amplified by the mysterious dark matter that pervades the cosmos, began to create pockets where the gas was slightly more concentrated. Gravity, the architect of cosmic evolution, took hold within these denser regions, pulling the gas inward. As these clouds of gas grew denser and hotter, they reached a critical threshold, igniting the nuclear fusion processes at their cores. This marked the birth of the first stars, colossal and bright, primarily composed of hydrogen and helium. These population 3 stars were giants compared to their modern counterparts, burning with such intensity that their lifespans were relatively brief on a cosmic scale. The ignition of the first stars introduced light back into the universe, ending the Cosmic Dark Ages. These stars were not solitary beacons. They began to clump together under gravity's relentless pull, forming the nuclei of the first galaxies. These early galaxies were smaller and less structured than the ones we see today, yet they were the seed from which the grand spirals and vast ellipticals of the current universe would grow. As these first stars aged, they played a crucial role in the chemical enrichment of the cosmos. The nuclear fusion processes at their hearts forged heavier elements like carbon, oxygen, and iron, elements that had not existed before. When these stars reach the end of their lives, they expel these heavier elements into space through supernova explosions, seeding the cosmos with the building blocks necessary for future generations of stars, planets, and eventually life. The formation of the first stars and galaxies set in motion a complex web of interactions that would shape the universe's evolution. The radiation from the first stars helped to reionize the surrounding medium, clearing the fog of the early universe and making it transparent to light. This process, known as cosmic reionization, was a gradual one, stretching from about 150 million to a billion years after Big Bang, and was essential for the universe to become the starlit expanse we observe today. As the first stars and galaxies began to illuminate the cosmos, an invisible scaffold was already in place, guiding their formation and distribution across the universe. This unseen framework is known as dark matter, a term that encompasses a vast portion of the universe's total mass. Unlike the stars, planets, and gas clouds that emit or reflect light, dark matter does not interact with electromagnetic forces, making it completely invisible to our current observational instruments. Despite its elusive nature, dark matter plays a crucial role in the cosmos, especially in the formation of large-scale structures like galaxies and galaxy clusters. The existence of dark matter was first inferred from the gravitational effects it has on visible matter. For instance, galaxies spin at such speeds that, without the presence of a significant amount of unseen mass, they would simply fly apart. Furthermore, the way galaxies cluster together, along with observations of the cosmic microwave background radiation, the afterglow of the Big Bang, suggests that there is far more matter in the universe than we can directly observe. Studies estimate that dark matter constitutes about 85% of the total matter in the universe, a figure that underscores its importance in cosmic evolution. Dark matter played a pivotal role in the formation of cosmic structures. In the early universe, slight density fluctuations became the seeds of the first structures to form. Dark matter, unaffected by anything but gravity, began to clump together in these denser regions, forming vast halos that would serve as gravitational wells, pulling in the normal or baryonic matter. This process accelerated the formation of stars and galaxies as hydrogen and helium gas fell into the gravitational pits carved out by dark matter. These dark matter halos provided the necessary gravitational framework for the gas to cool and condense into stars. As these stars formed and grouped into the first galaxies, they followed the underlying dark matter distribution, leading to the large-scale structure of the universe we see today, with galaxies and galaxy clusters woven into a cosmic web of filaments and voids. This structure, predicted by simulations that include dark matter, matches observations of a universe at large scales remarkably well. The role of dark matter in cosmic structure formation is a topic of ongoing research and fascination in cosmology. Its presence is inferred from its gravitational effects, yet its true nature remains one of the biggest mysteries in science. Formation of galaxies. Delving into the cosmic ballet of galaxy formation, we embark on a journey that spans billions of years, where the universe's fundamental forces choreograph the creation of these colossal celestial entities. Galaxies, vast islands of stars, gas, dust, and dark matter, are the building blocks of the cosmos, and their formation is a tale of both simplicity and complexity, woven by the laws of physics. In the beginning, following the Big Bang, the universe was a hot, dense sea of particles. As it expanded, temperatures dropped, allowing protons and electrons to combine and form neutral hydrogen atoms. This era, known as recombination, marked the universe's transition from opacity to transparency, allowing light to travel freely for the first time. However, the universe was not perfectly uniform. Slight density variations, or ripples in the fabric of space-time, left by the Big Bang, set the stage for galaxy formation. Gravity, the architect of the cosmos, took center stage, amplifying these tiny fluctuations. Regions slightly denser than their surroundings began to attract more and more matter, growing increasingly more massive. This process is beautifully illustrated by the concept of gravitational collapse, where gas clouds, primarily hydrogen, begin to collapse under their own gravity. As these clouds condense, They formed the first stars and protogalaxies, simple structures that would evolve into the complex galaxies we observe today. However, galaxy formation is not solely a product of gravity's inward pull. Other forces played pivotal roles, such as dark matter, a mysterious substance that does not emit, absorb, or reflect light but exerts gravitational effects on visible matter. Dark matter makes up about 85% of the universe's total matter content and acted as scaffolding for galaxy formation. It clumped together in the early universe, creating gravitational wells into which ordinary matter could fall, accelerating the process of galaxy assembly. Moreover, feedback processes, where energy from star formation and supernova explosions heated and expelled gas from early galaxies, also significantly influenced their evolution. These energetic outflows prevented the gas from cooling and collapsing too quickly, regulating the pace of star formation and leading to the diverse array of galaxy sizes and shapes observed today, from spiral galaxies like our Milky Way to elliptical and irregular galaxies. As galaxies grew, they did not evolve in isolation. Collisions and mergers between galaxies were common, especially in the crowded environment of the early universe. These cosmic encounters could dramatically alter a galaxy's structure and star formation rate, creating new morphological features, such as spiral arms, and seeding the growth of supermassive black holes at their centers. Today, galaxies continue to evolve, influenced by their interactions with their environment, including other galaxies and intergalactic gas. The study of galaxy formation and evolution not only sheds light on the history of the universe, but also provides crucial insights into the fundamental processes governing the cosmos. It's a narrative of creation, transformation, and interaction, highlighting the intricate dance of matter and energy that shapes our universe. In the vast expanse of the universe, galaxies are the grand assemblies of stars, gas, dust, and dark matter, presenting themselves in a variety of magnificent forms. These cosmic entities, numbering in the billions, are classified into several main types, each with its own unique characteristics and origins, painting a rich tapestry of the cosmos' diversity. Among these types, spiral, elliptical, and irregular galaxies stand out, each telling a different story of cosmic evolution and interaction. Spiral galaxies, such as our Milky Way, are distinguished by their flat, disc-like appearance, featuring swirling arms that emanate from a central bulge. This bulge is a dense concentration of older stars, around which the arms, sites of active star formation, wrap themselves in graceful arcs. These arms are rich in gas and dust, the raw materials for new stars, and are often highlighted by bright nebulae and young, hot stars that give them a distinct glow. The spiral pattern is thought to be a result of density waves that sweep through the galaxy, compressing gas and dust to spark star formation in a ripple effect. Elliptical galaxies, in contrast, lack the defined structure and spiral arms of their disc-shaped counterparts. They range from nearly spherical to elongated shapes and are composed mostly of older, redder stars, with minimal gas and dust. This makes them relatively barren in terms of new star formation. The size of elliptical galaxies can vary widely, from giants that dominate their local clusters of galaxies to dwarfs that flit like shadows around their larger neighbors. The formation of these galaxies is often attributed to the merging of smaller galaxies, a process that strips away gas and leaves behind a smoother, less structured formation. Irregular galaxies, as the name suggests, lack the coherent structure seen in spiral and elliptical galaxies. These galaxies are often chaotic in appearance, without a defined form, and are rich in gas and dust, making them fertile grounds for star formation. Their irregular shapes can be the result of gravitational interactions or collisions with other galaxies, which distort their structure and trigger bursts of star formation. These galaxies are important to astronomers as they often provide insights into the processes of galaxy interaction and evolution. Beyond these broad categories, there are also subtypes and peculiar galaxies that defy easy classification, often resulting from the dynamic and sometimes violent interactions between galaxies. For example, lenticular galaxies possess a large central bulge in the disk but lack the spiral arms, sitting in a category between spiral and elliptical galaxies. This diversity underscores the complexity of cosmic evolution and the influence of gravity, collision, and merger events in shaping the universe's structure. The story of the Milky Way formation is a cosmic saga that spans billions of years, weaving together the forces of gravity, the mysteries of dark matter, and the life cycle of stars. At the heart of this narrative is the concept of hierarchical assembly, a process by which smaller components merge to form larger structures, a principle that underpins the evolution of galaxies across the universe. Our Milky Way, a barred spiral galaxy with vast, swirling arms wrapped around a luminous core, began its life about 13.6 billion years ago, not long after the Big Bang. In the early universe, a period marked by a cosmic soup of hydrogen, helium, and traces of lithium, slight irregularities in density, perhaps influenced by the enigmatic nature of dark matter, began to coalesce under the relentless pull of gravity. These denser regions attracted more matter, growing into the first protogalaxies, the building blocks of modern galaxies. As these protogalaxies orbited each other, their mutual gravitational attractions pulled them closer, leading to a series of mergers. With each merger, the nascent Milky Way grew in size and complexity. The age of the Milky Way, our sprawling galactic home, is a topic that captures the imagination, offering a window into the ancient past of the universe itself. Through the diligent efforts of astronomers and astrophysicists, using a combination of observational data and theoretical models, we've come to understand that our galaxy is approximately 13.6 billion years old. This remarkable age places its formation not long after the Big Bang, which is estimated to have occurred about 13.8 billion years ago, making the Milky Way one of the universe's older galaxies. Determining the age of the Milky Way involves piecing together evidence from various sources. One of the key methods scientists use is studying the oldest stars within the galaxy. By measuring the abundances of different elements in these stars, researchers can infer their ages. Older stars have fewer heavy elements, as these were formed in the cores of stars and distributed into space as stars died, enriching the galaxy with the material for new stars. The ages of these ancient stars, many found in the galaxy's halo and in globular clusters, offer clues to the Milky Way's early years. Another approach to gauging the galaxy's age comes from understanding the age of the universe itself, derived from observations of the cosmic microwave background radiation, the afterglow of the Big Bang, and the expansion rate of the universe. By comparing the age of the oldest stars with the age of the universe, scientists can confirm that the Milky Way formed early in cosmic history. The age of the Milky Way not only tells us about the longevity of our galaxy, but also provides insights into the processes of galaxy formation and evolution. It suggests that the Milky Way began forming soon after the dawn of the universe, growing over billions of years through the accumulation of gas, the formation of stars, and the merging with other galaxies. This gradual assembly process, influenced by the mysterious dark matter that pervades a galaxy, has shaped the Milky Way into the spiral galaxy we observe today. Understanding the age of the Milky Way also puts into perspective the cosmic timeline on which astronomical events occur. For instance, the Sun, around 4.6 billion years old, is a relatively young addition to the galaxy, highlighting the ongoing nature of star formation and the dynamic evolution of the Milky Way. The galactic center is a term that evokes a sense of intrigue and mystery, pointing us towards a dense, luminous heart of the Milky Way. This region, bustling with astronomical activity, is located about 27,000 light-years from Earth and houses a remarkable array of cosmic phenomena, central to which is Sagittarius A*, SGR A*, a supermassive black hole that serves as a dynamo at the core of our galaxy. With a mass equivalent to about 4 million times that of our Sun, SGR A* is a gravitational anchor around which the galaxy's vast spiral structure coalesces. Surrounding this enigmatic black hole is a bustling environment of stars, gas clouds, and other astronomical objects, all tightly packed into a relatively small volume of space. This region teems with a variety of stars, from young, hot blue stars that blaze with intense brightness to older, cooler stars that have orbited the galactic center for billions of years. The presence of young stars in such a hostile environment, close to a supermassive black hole, puzzles astronomers, as the tidal forces exerted by the black hole should theoretically tear apart the gas clouds from which stars form. Yet, their existence suggests that star formation processes in the galactic center are somehow different from those in the galaxy's less tumultuous regions. In addition to stars, the galactic center is awash with vast clouds of gas and dust, some of which are in the process of being pulled into SGR A*, while others may be forming new stars. The region is also crisscrossed by filaments of magnetic energy and bathed in the intense radiation emitted by the accretion of material onto the supermassive black hole, creating a dynamic and complex astrophysical laboratory. The area around the galactic center is also the source of various high-energy phenomena, including flares and other emissions resulting from the interaction of SGRA* with its surroundings. These events provide astronomers with valuable insights into the physics of black holes and the mechanisms of energy transfer in the extreme conditions near galaxies' core. Observing the galactic center is a challenging endeavor due to the vast amounts of interstellar dust that lie between it and Earth, which obscure our view in visible light wavelengths. However, astronomers have employed radio, infrared, and X-ray telescopes to pierce through this veil of dust, revealing the center's complex structure and activity. These observations have not only confirmed the presence of the supermassive black hole, but have also allowed scientists to study the properties of SGRA* and its impact on the galactic center's environment. The Milky Way, our grand spiral galaxy, does not exist in isolation in the vast expanse of the universe. It is accompanied by a retinue of smaller satellite galaxies, each with its own unique characteristics and trajectory, yet all are bound to the Milky Way by the invisible tethers of gravity. These interactions between the Milky Way and its satellites are not merely distant, passive relationships, but are dynamic and, at times, tumultuous, playing a significant role in the evolution of our galaxy. Among the most notable of these satellite galaxies are the large and small Magellanic Clouds, visible from the southern hemisphere. These dwarf galaxies, rich in gas and dust, are in a close gravitational dance with the Milky Way, one that has implications for the structure and future of all the galaxies involved. As they orbit our galaxy, gravitational forces act between the Milky Way and the Magellanic Clouds, resulting in phenomena such as tidal stripping, where gas is pulled away from the satellite galaxies. This stripped gas can feed into the Milky Way, contributing to the reservoir of material from which new stars form. Moreover, the interaction between the Milky Way and its satellites is not a one-way street. The gravitational pull of the Magellanic Clouds, for example, has been implicated in the warping of the Milky Way's disk, a subtle yet telling indication of the interconnectedness of cosmic structures. Peering into the future of the Milky Way galaxy unveils a narrative rich with cosmic evolution and dramatic transformations. As astronomers gaze through their telescopes and run simulations on powerful computers, they forecast a future in which the Milky Way undergoes significant changes, shaped by the inexorable forces of gravity, the ongoing process of star formation, and impending galactic collisions. One of the most monumental events predicted to occur in the Milky Way's future is its collision with the Andromeda Galaxy. Currently, Andromeda, also a spiral galaxy like the Milky Way, is about 2.5 million light-years away but is moving towards us at about 110 kilometers per second. In approximately 4 billion years, the skies above Earth, or any planet hosting observers at that time, will bear witness to this grand cosmic merger. As these two galaxies begin to intertwine, their mutual gravitational forces will draw them closer, eventually merging into a single, larger elliptical galaxy, sometimes humorously dubbed Milkometer or Milkydromeda in scientific discussions. The solar system and Earth, the formation of the solar system, is a captivating chapter in the story of the cosmos, revealing the processes that led to the creation of our sun, the planets, and the myriad smaller bodies that orbit our star. This cosmic tale began around 4.6 billion years ago, in a dark corner of the Milky Way, when a vast cloud of gas and dust, known as a solar nebula, started to collapse under its own gravity. Throughout billions of years, the solar system has been a dynamic and evolving place, marked by collisions and migrations that have shaped the planets and their orbits. The Late Heavy Bombardment, a period of increased comet and asteroid impacts about 3.8 billion years ago, is one example of the dramatic events that have left their mark on the solar system. In understanding the formation of the solar system, scientists rely on a combination of observational data, computer simulations, and the study of meteorites, which provide direct evidence of the early solar system's composition. These investigations not only shed light on our cosmic origins, but also offer insights into the formation of other planetary systems across the galaxy. The Milky Way, our galaxy, played an indispensable role in the formation of the solar system, setting the stage for the series of events that led to the birth of the Sun and its surrounding planets, moons, asteroids, and comets. This grand cosmic narrative is rooted in the Milky Way's vast reservoirs of gas and dust, its gravitational forces, and the life cycles of its stars, which together foster the conditions necessary for the solar system's emergence about 4.6 billion years ago. At the heart of the solar system formation story is the interstellar medium of the Milky Way, a mixture of gas, mostly hydrogen, and helium, along with dust. This medium, enriched over billions of years by the remnants of dead stars, provided the raw materials from which the solar system was formed. Supernovae, the explosive deaths of massive stars, played a crucial role by seeding the galaxy with heavy elements like carbon, oxygen, and iron, which are essential for formation of rocky planets and the development of life on Earth. The Milky Way's gravitational landscape also influenced the solar system formation. The galaxy's spiral structure, characterized by its rotating arms, is thought to trigger the formation of new stars as it sweeps through the interstellar medium, compressing gas and dust. It's within such a dynamic environment that our solar system found its origin, in a dense region of molecular cloud, where the conditions were just right for the solar nebula, the cloud of gas and dust that collapsed to form the Sun and its planets, to coalesce. Furthermore, the Milky Way's chemical composition, a record of its history of star formation and death, provided a critical backdrop. The particular mix of elements available in the region of the galaxy where the solar system formed influenced the types of planets that could emerge. The inner, rocky planets, Mercury, Venus, Earth, and Mars, formed from materials that could condense at high temperatures close to the young Sun. In contrast, the gas giants and ice giants formed farther out, where cooler conditions allowed for the accumulation of volatile compounds. The solar system's location within the Milky Way is another aspect of the galaxy's role in its formation. Situated in the Orion Arm, a relatively quiet region between the major spiral arms, the solar system has been spared from the intense radiation and gravitational disturbances that might disrupt planetary systems closer to the galaxy's bustling center. This stable environment has been conducive to the development and persistence of life on Earth, providing a vantage point from which we can observe and study the galaxy and the broader universe. The formation of Earth is a chapter in the grand narrative of the solar system's birth, unfolding over 4.6 billion years ago within the swirling disk of gas and dust known as the solar nebula. This process, driven by the laws of physics and the dynamic environment of the early solar system, led to the creation of our home planet, a world uniquely suited for life as we know it. As the solar nebula collapsed under its own gravity, it spun faster and flattened into a disk. At the center, the Sun began to form, igniting its nuclear furnace and casting light and heat out into the surrounding space. In the cooler regions of the disk, far enough from the young Sun's warmth, particles of dust and ice began to stick together as they collided, forming clumps that grew into larger bodies over time. These early building blocks of the planets, known as planetesimals, continued to collide and merge, driven by their mutual gravitational attraction. In a process termed accretion, these planetesimals gradually built up the rocky cores of the inner planets, including Earth. This early phase of Earth formation was marked by intense bombardment as it grew through the accumulation of material, reaching about 60% of its current size relatively quickly, in a few tens of millions of years. As Earth grew, its interior heated up due to the energy released from these collisions, along with the decay of radioactive elements within its materials. This heat caused the young Earth to partially melt, allowing it to differentiate into layers: a dense, metallic core, a silicate mantle, and a crust on the surface. The formation of Earth's core was crucial for generating the planet's magnetic field, which plays a key role in protecting the surface from harmful solar and cosmic radiation. Meanwhile, the intense heat and volcanic activity released gases trapped in the rocks, contributing to the formation of Earth's early atmosphere. Water vapor, carbon dioxide, methane, and ammonia were among the gases released, creating a primordial atmosphere very different from the one we breathe today. Water vapor in the atmosphere eventually condensed as the Earth cooled, falling as rain and filling the basins that formed on the planet's surface, creating the oceans. The presence of liquid water, essential for life, along with the stability provided by Earth-sized orbit and a protective magnetic field, set the stage for the eventual emergence of life. Over billions of years, Earth's atmosphere and surface evolved. The emergence of life, particularly photosynthetic organisms, transformed the atmosphere, increasing the amount of oxygen and making it hospitable to a diverse range of life forms. These biological and geological processes have continued to shape Earth, making it the dynamic, life-supporting planet we know today. The emergence of life on Earth, a planet teeming with diverse forms of organisms, is a result of a unique combination of conditions and events that unfolded over billions of years. These conditions, ranging from the planet's placement in the solar system to the composition of its atmosphere and oceans, created an environment conducive to the development and sustenance of life as we know it. One of the most fundamental conditions that made life possible on Earth is its location in the solar system, often referred to as the Goldilocks zone or the habitable zone. This region is not too close to the sun, where it would be too hot for liquid water to exist, and not too far, where it would be too cold. Earth's orbit within this zone allowed for the presence of liquid water on its surface, a critical ingredient for life. The formation of Earth's atmosphere was another crucial step in creating a habitable planet. Initially composed of gases released from volcanic eruptions, such as water vapor, carbon dioxide, and ammonia, the atmosphere underwent significant changes over time. The emergence of photosynthetic organisms, which could convert carbon dioxide and water into oxygen and glucose using sunlight, gradually increased the oxygen levels in the atmosphere. This oxygen-rich atmosphere not only supported the development of new life forms, but also formed the ozone layer, which protects the surface from harmful ultraviolet radiation from the Sun-Earth's magnetic field, generated by the movement of molten iron in its outer core, shields the planet from solar and cosmic radiation that could strip away the atmosphere and harm living organisms. Advanced topics. Dark energy, a term that evokes mystery and intrigue, plays a pivotal role in the cosmos, fundamentally influencing the universe's fate and structure. This enigmatic force, which makes up about 68% of the universe, is responsible for the accelerated expansion of the universe, a discovery that has reshaped our understanding of cosmology since it was first observed in the late 1990s. The concept of dark energy emerged from observations of distant supernovae, which show that galaxies are moving away from each other at an accelerating rate, contrary to the expectation that the universe's expansion should be slowing down due to gravity. This acceleration suggested the presence of an unknown form of energy that permeates all of space, exerting a repulsive force that overcomes gravity on cosmological scales. In conclusion, the formation and evolution of the solar system are deeply intertwined with the vast processes of the Milky Way galaxy, from the distribution of interstellar material to the influence of gravitational forces and stellar life cycles. Earth's unique position in the habitable zone, its geological activity, atmosphere, and presence of liquid water have made it a cradle for life, while the stability provided by the moon and magnetic field has ensured its long-term sustainability. Furthermore, dark energy, an enigmatic force driving the accelerated expansion of the universe, continues to challenge our understanding of cosmology, shaping the very fabric of space and time. By studying these cosmic phenomena, we not only gain insights into our own origins, but also expand our knowledge of planetary formation, the potential for life beyond Earth, and the ultimate fate of the universe.